Usually when you get a medical diagnosis, there's this, I don't know, this expectation of mechanical precision, like
Yeah.
if you fracture your arm, the x-ray shows this jagged white line on a black background, and the doctor just points to it and says, there's the problem. Here's your plaster cast.
Right, it's very binary. Broken or unbroken, we really crave that visibility.
Exactly. We want biological problems to just behave like engineering problems.
Yeah.
But the moment you step into the world of oncology, and specifically the landscape of breast cancer treatment, that whole reassuring x-ray machine concept just shatters.
Oh, absolutely. You are no longer dealing with binary engineering at that point.
No, not at all. We are navigating a diagnostic and therapeutic environment that is just incredibly murky, constantly mutating, and, well, staggeringly complex. And we're always looking for the next billion-dollar, heavily engineered synthetic molecule to fix it.
Because the standard assumption in modern medicine is that massive complex diseases require massive, complex, and usually wildly expensive solutions.
Which is exactly why the research we're unpacking today is so disruptive. Welcome to the Deep Dive. Today we're looking at a fascinating analysis from a platform called Biotechnology Guy.
Right, founded by Shubham Thorat.
Yeah, he's a biotechnologist and web developer who has this real knack for translating dense clinical data into accessible science. And the core mission of our deep dive today is to explore a truly paradigm-shifting concept in oncology.
It really is. The idea that something sitting quietly in the supplement aisle of your local grocery store might significantly amplify standard breast cancer treatment.
Right, a substance that costs a few dollars, something that doesn't require a specialized pharmacy, yet it's making these huge waves in clinical trials.
But, to really appreciate the gravity of a cheap supplement altering cancer outcomes, we first have to understand the sheer scale of the battlefield.
Yeah, we have to look at the brutality of the current standard of care.
Yeah.
Because the specific hurdles that both oncologists and patients face happen long before an operating room is ever prepped.
And the source material lays out the baseline statistics perfectly. They're sobering, honestly, no matter how many times you hear them.
Breast cancer is the most commonly diagnosed cancer globally.
Yeah.
I mean, we're looking at an incidence rate where 1 in 8 women will develop it in their lifetime.
And if you translate that into annual figures, it gives us around 2.3 million new cases diagnosed every single year.
2.3 million. And despite decades of immense funding, public awareness campaigns and genuine leaps forward in targeted therapies, the mortality rate is still devastating.
Over 670,000 people die from breast cancer annually.
So when a patient enters that cohort of 2.3 million, the instinct is visceral and immediate, right? Just surgically remove the tumor, cut it out.
Sure, but clinical reality rarely permits a straight line like that. Often, the protocol demands a pretty grueling detour before surgery is even an option.
Which introduces the foundational clinical concept for our discussion today, neoadjuvant chemotherapy. Let's unpack that jargon for everyone.
Right, so adjuvant therapy is what we traditionally think of. That's the treatment given after the primary surgical intervention to sweep up microscopic disease and lower the risk of recurrence.
But the prefix neo flips the timeline.
Exactly. Neoadjuvant chemotherapy is systemic chemical warfare waged before the surgeon ever makes an incision.
And oncologists deploy this strategy for some highly specific biological and mechanical reasons, don't they?
They do. Primarily, it's used when a tumor is simply too large or too entangled with surrounding vital structures to safely resect.
Like if it's invaded the chest wall or involves the lymph nodes.
Right. If you do immediate surgery, then you risk leaving significant macroscopic disease behind or just causing unacceptable physical trauma to the patient.
So the chemotherapy serves as the vanguard.
Yeah.
You're pumping these systemic toxins into the body to chemically assault the bulk of the mass.
Shrinking it down to a manageable size so that the surgical margins become achievable. The intention is to downgrade the surgical requirement.
Like turning a necessary mastectomy into a breast-conserving lumpectomy. You're trying to destroy the maximum volume of malignant cells before you attempt the physical extraction.
That's the goal.
I always conceptualize this, like trying to salvage a piece of clothing with a deeply set, polymerized grease stain. You don't just throw it into the washing machine on a standard cycle and expect clean fabric.
Now you have to pre-treat it.
Exactly. The washing machine is the surgery. But before you do that, you apply heavy-duty caustic chemical solvents. You let them soak into the fibers, and you try to break down the worst of the binding agents.
You let the chemicals do the heavy lifting so that the mechanical action of the washing machine can actually finish the job. It's a great analogy, especially when you consider the toxicity involved here.
Right, because these aren't gentle chemicals.
Not at all. You are deliberately introducing highly aggressive agents, things like anthracyclines, taxanes, into the entire systemic circulation just to attack localized tissue.
Which actually leads me to a really big question. Let me
Uh-huh.
push back on this a bit.
Sure, go ahead.
If these agents are powerful enough to shrink a massive, entrenched tumor, why do we even need the washing machine at all? If neoadjuvant chemo is designed to eradicate cancer cells, why isn't the chemical bombardment just the end of the line? Why is surgery still the primary event?
It's a great question, and it comes down to the fact that tumors are not just homogeneous blocks of identical cells. They are incredibly chaotic, highly evolved, microscopic ecosystems.
Meaning there's a lot of genetic variety in there.
Massive genetic heterogeneity within a single tumor mass. You might have an outer layer of rapidly dividing cells that are highly susceptible to the chemotherapy.
So the drugs enter the blood supply, hit those outer cells, and cause massive shrinkage.
Right. But deeper inside the mass?
These get complicated.
Very. Deeper inside, the blood vessels are often abnormal and compressed, meaning the drugs physically cannot penetrate effectively.
Oh, wow. So the plumbing is literally broken inside the tumor.
Exactly. Furthermore, cancer cells are notorious for mutating under pressure. You have slow-growing clones in there, or cells that have upregulated specific pump mechanisms to literally spit the chemotherapy drugs back out of their cytoplasm.
That is terrifying. They just pump the poison right back out.
Yeah. So the neoadjuvant chemo acts as an evolutionary bottleneck. It kills off the vulnerable 90% of the tumor, but it leaves behind the most hardened, resistant, and stubborn clones.
The residual disease, the survivors of the chemical fire.
And if you leave those survivors in the body, they will inevitably repopulate. And when they do, the resulting tumor will be entirely composed of cells that have already proven they can survive your best chemotherapy drugs.
Ah, so the surgery is the indispensable mechanical sweep required to excise those hardened remnants.
You absolutely have to get them out.
Understanding that stubborn resilience really leads us directly to what the surgical team and the pathologists are desperately looking for once that tissue is removed.
Because the surgery isn't just about extraction, it is the ultimate diagnostic verdict on how successful that months-long
Primary tumor bed and the surrounding lymph nodes, that provides the definitive measure of the patient's prognosis.
And this is where we encounter arguably the most critical acronym in oncology literature and really the focal point of the Biotechnology Guy article.
PCR.
Yes, pathological complete response.
This is the holy grail. I mean, after the patient has endured months of hair loss, severe nausea, immune suppression, and just overwhelming fatigue, the surgeon removes the tissue and sends it to the pathology lab.
The pathologist sections the tissue microscopically thin, stains it, and scrutinizes it under high magnification.
And achieving PCR means the pathologist is looking at those slides and finding absolutely nothing.
Zero evidence of invasive cancer.
Wow.
No residual malignant cells in the primary breast tissue, and crucially, no cancer cells hiding in the regional lymph nodes.
So the neoadjuvant chemotherapy didn't just shrink the tumor, it eradicated it on a cellular level.
Completely wiped it out.
Going back to that eviction analogy we often hear in medicine, a partial response means the destructive tenant, the tumor was forced out, but they trashed the property.
They left damage behind. Maybe a few of their associates are still hiding in the closets.
Right, the closets being the lymph nodes. But achieving PCR means not only did the tenant leave, but the house was professionally sterilized. There is no biological footprint left behind.
And the distinction is vital because it directly dictates survival curves. Patients who achieve pathological complete response have significantly superior long-term outcomes.
Because the microscopic threat is gone.
Exactly. Their risk of systemic recurrence drops dramatically, and their overall survival rates skyrocket compared to patients who have residual invasive disease at the time of surgery. It's the most robust prognostic indicator we have following neoadjuvant therapy.
But the reality of current oncology is that most patients never reach that baseline. I mean, the data in the article shows that PCR is just frustratingly elusive.
It really is. The rates are highly variable and often quite discouraging. Depending on the specific biological subtype of the breast cancer and the specific chemotherapeutic regimen used, PCR rates generally hover between 20% and 60%.
That is a staggering variance, 20 to 60. So if we look at the high end, 60% might be achievable for highly aggressive but chemosensitive subtypes.
Right, like certain triple negative or HER2 positive breast cancers, especially when targeted therapies are added to the mix.
But for estrogen receptor-positive tumors, which tend to be slower growing and therefore less responsive to traditional cell cycle-dependent chemo, the PCR rate can sit firmly at the bottom of that barrel.
Closer to 10 or 20%, yeah.
So we have a scenario where up to 80% of certain patient populations are willingly enduring 6 months of systemic toxicity, clinging to the hope of eradication, only to wake up from surgery and be told they still have active mutating cancer cells inside them.
The psychological toll of that shortfall is almost unimaginable.
It has to be.
And it drives an immense sense of urgency within the research community. Pharmaceutical pipelines are dominated by the pursuit of novel agents, immunotherapies, antibody-drug conjugates, PRP
All
inhibitors,
designed to just squeeze those PCR rates a little bit higher.
because every single percentage point increase translates directly to thousands of women avoiding recurrence and death.
And these novel agents almost universally come with astronomical development costs, complex administration protocols, severe side effects, and price tags that can, frankly, bankrupt healthcare systems.
Which brings us to the Brazilian clinical trial highlighted by Biotechnology Guy, a study that bypassed that multi-billion-dollar pharmaceutical pipeline entirely.
To test an intervention that is profoundly simple. Let's really dissect this study. It was conducted by researchers at the Botucatu School of Medicine at São Paulo State University.
Also known as FMBU NESP, yeah, with funding from FAPESC, which is a major Brazilian research foundation.
So they constructed a straightforward but highly revealing clinical trial. They enrolled a cohort of 80 women all over the age of 45 who were newly diagnosed with breast cancer and scheduled to undergo standard neoadjuvant chemotherapy.
And the demographic choice there is notable. Selecting women over 45 implies a cohort that is largely perimenopausal or postmenopausal.
Which has huge implications, right? Not just for the hormonal profile of their specific breast cancers, but also for their baseline bone density and their intrinsic vitamin D synthesis capability.
Exactly, because natural vitamin D synthesis declines with age. It creates a specific, highly relevant baseline for the study.
So the researchers took these 80 patients and divided them into 2 equal arms of 40.
And every single woman in both arms received the gold standard neoadjuvant chemotherapy protocol dictated by her specific tumor biology. The standard of care was strictly maintained across the board.
The divergence happened entirely in the supplementation.
Right. One arm of 40 women received their standard chemotherapy alongside a daily oral supplement of 2,000 international units of vitamin D3.
And the other arm.
The other arm received their standard chemotherapy alongside an identical placebo.
Now, the use of a double-blind, randomized controlled trial here in RCT is critical to emphasize, especially when we are talking about outcomes as consequential as tumor eradication.
It's the gold standard for a reason. In oncology, expectation bias can subtly skew how side effects are reported or how aggressively a patient adheres to a grueling chemo regimen.
So by blinding both the clinicians and the patients, the researchers isolated the biological variable.
Precisely. If there is a difference in the tissue under the microscope 6 months later, it cannot be attributed to the placebo effect or clinical bias. It has to be the molecular action of the supplement.
And the specific nomenclature used in the article for the supplement is also important. They specify cholecalciferol, in parentheses, next to vitamin D3. Let's break that down.
Well, cholecalciferol is the specific biologically relevant compound. It distinguishes it from ergocalciferol, or vitamin D2, which is plant-derived.
Cholecalciferol being the animal-derived form.
Right. It's the exact molecular structure our own skin synthesizes upon UVB radiation exposure. It has a significantly higher efficacy in raising and maintaining serum levels of the active hormone in the human bloodstream.
Okay, so with the variables tightly controlled, these 80 women progressed through their 6 months of neoadjuvant therapy. Following the conclusion of the chemical phase, they all proceeded to surgical resection.
And the excised tissues were handed over to the pathologists, who were entirely blind to which arm the patients belonged to, and they began the search for residual disease.
And the results of those pathology reports are what elevate this from a footnote to a potential paradigm shift.
In the control arm, the 40 women who received standard chemotherapy plus the placebo, 24% achieved pathological complete response.
Okay, so that 24% aligns perfectly with the lower end of the established global baseline we discussed earlier.
Right. The chemotherapy performed exactly as the historical data suggested it would.
But then we look at the experimental arm.
The 40 women who received the standard chemotherapy plus the daily 2,000 IU dose of cholecalciferol In that group, 43% achieved pathological complete response.
A jump from 24% to 43%. We were talking about nearly doubling the rate of total tumor eradication just by adding a basic daily supplement to the regimen.
It's incredible. One of the study authors, Eduardo Carvalho Pessoa, noted that even within the constraints of a small participant sample, the difference observed was highly statistically significant.
I mean, a 43% PCR rate is the kind of number that usually requires a newly patented $150,000 a year monoclonal antibody to achieve. Seeing it triggered by a bottle of vitamins is jarring.
It really is.
But as anyone who regularly reads clinical oncology literature knows, we have to look very carefully at how these numbers are presented. The biotechnology guy analysis specifically points out the mathematical framing here.
Yes, needing a 79% difference in relative terms, but an absolute difference of 19 percentage points.
And this distinction between relative and absolute outcomes is where so much of the public misunderstanding of medical science occurs.
Completely. When clinical trial data is press released, the spotlight is almost exclusively shown on the relative difference.
Because 79% sounds like a revolution. It sounds like a cure.
Exactly. But relative difference is a proportional comparison. It takes the baseline PCR rate of 24% and asks, how large is the increase relative to that starting point?
So the increase was 19 percentage points. And since 19 is roughly 79% of 24, the relative increase in success is 79%.
It's a mathematically accurate way to describe proportional growth, but it entirely strips away the real-world context of the baseline risk.
It's like a financial analogy I use. If you have $1 and I give you another dollar, your absolute wealth increased by just $1. But your relative wealth just jumped by 100%. Context is everything.
That's a perfect way to put it. Or think about rare genetic mutations. If a mutation increases your baseline risk of a disease from 1 in 100,000 to 2 in 100,000, your relative risk has increased by 100%.
Your risk had doubled.
Right, but your absolute risk only went up by a single fraction of a percent. It remains statistically negligible to your daily life.
So absolute difference gives you the unvarnished clinical reality. It's the simple subtraction of the two outcomes. 43% minus 24% equals a 19 percentage point absolute difference.
Meaning out of 100 hypothetical women walking into that clinic, 19 more of them will walk out of surgery completely cancer-free because of the intervention.
And in the realm of oncology, a 19-point absolute gain is actually massive. Pharmaceutical companies routinely pop champagne over new drugs that offer a 3 or 4 percentage point absolute improvement.
Oh, absolutely. So a 19-point absolute gain is more than worthy of the attention.
However, let me play devil's advocate here. We have to address the glaring vulnerability of the Brazilian study. The sample size, 80 patients. That seems like a really tiny group for a cancer study. Can we actually trust a sample size that small to change how we treat cancer?
It's a very valid concern. 80 patients is small. In a phase 3 clinical trial, you want thousands of patients across dozens of different geographical centers.
Right, because with only 80 people, the statistical power is quite low. The risk of random chance, like a statistical fluke where you just happen to randomize more chemosensitive tumors into the vitamin D arm, is a real threat to the conclusion.
Exactly. A single pilot study with an N of 80 is a hypothesis generator, not a clinical mandate. To trust a signal this profound, you require corroborating data from independent cohorts. You need to see the mechanism replicated.
Which is what makes the inclusion of the Turkish trial in the source text so vital. The researchers didn't just observe the Brazilian anomaly. They pointed to a much larger, more robust set of data from Turkey that explored the exact same dynamic.
And the Turkish trial expanded the parameters significantly. They analyzed a cohort of 227 breast cancer patients undergoing neoadjuvant chemotherapy.
That is nearly triple the sample size.
Yeah.
And operating in a different healthcare system, on a different continent, likely with distinct genetic and environmental backgrounds among the patient population.
And the findings in the Turkish cohort mirrored the Brazilian signal with remarkable fidelity.
What did they find?
They observed that patients who maintained normalized vitamin D levels during their chemotherapy regimen were more than twice as likely to achieve complete pathological response compared to those who remained deficient.
Wow. Twice as likely maps almost perfectly onto the relative gains seen in Brazil.
It really does. Furthermore, the article notes that these prospective randomized trials are supported by decades of retrospective epidemiological data.
Meaning older observational studies.
Right. Older studies have consistently demonstrated a strong correlation between baseline vitamin D deficiency and poorer clinical outcomes in breast cancer. Things like higher rates of metastasis, shorter disease-free intervals, and higher overall mortality.
So when you combine decades of retrospective observational data showing the deficiency is dangerous, with multiple independent randomized prospective trials showing that supplementation actively drives tumor eradication, you transition away from a statistical fluke.
You are looking at a robust, undeniable biological pattern.
The pattern is established, and the clinical signal is loud enough that it demands we ask the fundamental molecular question: how?
How does an over-the-counter supplement exert enough biological force to fundamentally alter the architecture and survivability of a malignant tumor?
Right, because chemotherapy works by physically shredding DNA during cell division, or crippling the microscopic scaffolding of the cell. What is the molecular mechanism of a vitamin?
To understand the how, we have to completely deconstruct our understanding of what this substance actually is. The source text dives into the microscopic mechanisms, and it starts with a critical correction of nomenclature. The term vitamin D is actually biologically inaccurate.
It's a historical misnomer, isn't it? From the early 20th century when it was first discovered and grouped with other dietary factors.
Exactly. By definition, a true vitamin like vitamin C is an essential micronutrient that the human body cannot synthesize on its own. You must acquire it exogenously through diet. If you lack it, biological processes fail, resulting in scurvy.
But the human body is perfectly capable of synthesizing cholecalciferol endogenously.
Yes. When ultraviolet B radiation from sunlight strikes the skin, it triggers a photosynthetic reaction, converting a cholesterol derivative 7-dehydrocholesterol into pre-vitamin D3, which then isomerizes into cholecalciferol.
So it's synthesized in one organ, enters the systemic circulation, and travels to distant tissues to regulate biological function.
Which is the exact textbook definition of a hormone. Vitamin D does not function as a dietary cofactor, it functions as a master steroid hormone.
And the journey from the skin of the tumor cell is complex. The cholecalciferol generated by the skin or absorbed from that supplement pill is initially biologically inert, right?
Yeah.
It has to be activated.
Correct. It undergoes a two-step hydroxylation process. First, the liver processes it into 25-hydroxyvitamin D, which is the major circulating form we measure in blood tests.
But it still isn't fully active.
No. It then travels to the kidneys, where an enzyme converts it into 1025-dihydroxyvitamin D.
Also known as calcitriol.
Yes, calcitriol is the potent, active hormonal molecule. This is the entity that actually exerts biological force against the cancer cells.
The mechanism of that force is what I find most fascinating. The text details how calcitriol interacts with the body, and it centers entirely on the VDR.
The vitamin D receptor.
Right, so what exactly is the VDR?
The VDR is a specific protein structure found on the surface and within the cytoplasm of cells throughout the body, including almost all breast tissue cells, and critically, breast cancer cells.
Okay, so you can visualize the calcitriol hormone as a highly complex, uniquely milled physical key circulating in the bloodstream. And the VDR is the specific lock designed to accept only that key.
That's a great way to picture it. When calcitriol successfully binds to the VDR on a cancer cell, it forms a receptor-ligand complex. And this complex does not merely trigger a surface reaction. It physically translocates across the nuclear membrane and enters the nucleus of the cell.
The protected vault where the genomic blueprint is stored.
It bypasses the cytoplasmic signaling cascades and goes straight to the mainframe.
Wow, and once it's in there?
Once inside the nucleus, the calcitriol VDR complex acts as a transcription factor. It physically binds to specific regulatory sequences on the DNA strands known as vitamin D response elements.
So it is directly regulating gene expression. Like our DNA isn't a static, unchangeable architectural blueprint. It operates more like an immense control room filled with thousands of dimmer switches.
Exactly.
And every switch dictates a specific cellular behavior, synthesizing a protein, initiating division, triggering an immune alert. The calcitriol complex acts as a master director in that control room. It walks down the genomic aisles, aggressively turning certain switches all the way up and completely shutting other switches down.
That process, upregulating and downregulating specific genes, profoundly alters the behavior of the cell. And the Biotechnology Guy article explicitly lists the specific cellular pathways that this director takes control of: cell growth, apoptosis, immune response, inflammation, and angiogenesis.
Let's really break down each of those pathways to understand the full scope of the assault on the tumor, starting with cell growth. because cancer is fundamentally defined by unregulated runaway cellular proliferation.
Right. When calcitriol binds to the DNA, it downregulates the genes responsible for driving the cell cycle forward. It essentially forces the cancer cell to arrest in the G0, G1 phase of division.
It applies a severe biological brake to the uncontrolled multiplication. It stops the army from drafting new soldiers.
It's exactly what it does, but it doesn't just halt the growth, it actively engages in demolition. That brings us to the next pathway, apoptosis.
Apoptosis, which is programmed cell death, right?
Yes. It is an exquisitely controlled, highly organized physiological process. In a healthy organism, when a cell detects severe DNA damage, viral infection, or catastrophic structural failure, it doesn't just burst and cause inflammation.
Because that would damage surrounding tissue.
Right. Instead, it activates a cascade of enzymes called caspases. These enzymes meticulously dismantle the cell from the inside out, shredding the DNA and packaging the cellular debris into neat vesicles that the immune system can safely consume and recycle.
It is the ultimate cellular self-destruct button, designed to protect the whole organism from a rogue cell.
But malignant cells are exceptionally dangerous because they have successfully mutated to disable or ignore that self-destruct sequence. They sustain massive DNA damage but continue to divide, effectively achieving biological immortality.
And here comes calcitriol. The complex enters the nucleus and forcefully upregulates the genes that control apoptosis. It essentially repairs the wiring on the broken self-destruct button and leans on it, forcing the malignant cells to recognize their own catastrophic mutations and initiate their own death sequences.
It's brilliant, and while it's doing that, it's simultaneously altering the environment around the tumor. The text mentions immune response and inflammation.
How does it handle that?
Calcitriol modulates the tumor microenvironment by dialing down the chronic pro-tumorigenic inflammation that often acts as a fertilizer for cancer cells, while simultaneously upregulating the activity of macrophages and natural killer cells, recruiting them to recognize and attack the malignant tissue.
So it calls in the cavalry while putting out the fires that are feeding the tumor. But the final mechanism on that list might be the most devastating to a solid tumor: angiogenesis.
Angio, referring to blood vessels, and genesis meaning creation, the formation of new blood vessels.
Right, because when a tumor initially forms, it can survive by scavenging oxygen and nutrients from the immediate surrounding tissue. But once it grows beyond a few millimeters in diameter, the cells deep inside the mass begin to suffocate.
To continue expanding, the tumor must secure its own dedicated logistics network.
And how does it do that?
It does this by secreting massive amounts of pro-angiogenic factors, primarily a protein called VEGF, vascular endothelial growth factor. This protein acts as a chemical distress signal that hijacks the body's normal vascular system, commanding nearby blood vessels to sprout new capillaries that grow directly into the tumor mass.
So it builds a private, dedicated pipeline to siphon off the host's blood, oxygen, and glucose. Without angiogenesis, a tumor's growth is fundamentally capped. It cannot progress.
Exactly, and calcitriol heavily downregulates the expression of VEGF and other angiogenic factors. It acts as a powerful anti-angiogenic agent.
So it severs the supply lines, it isolates the tumor, starving it of the oxygen and glucose it requires to fuel its runaway metabolism.
That's right. So if we synthesize this molecular activity, the hormone halts cellular division, forces malignant cells into programmed suicide, recruits the immune system for a targeted attack, and chokes off the tumor's vascular supply lines.
Which raises a very logical objection. Let me ask you this. If this hormone is orchestrating such a comprehensive, multi-front assault on the cancer, why do we even need the chemotherapy? If calcitriol is starving it, stopping its growth, and triggering its self-destructive mechanisms, why isn't vitamin D just a standalone cure?
That's a fair question, but the distinction lies in the nature of the mechanism. Calcitriol is a potent biological modulator, but it is not a direct cytotoxic agent in the way standard chemotherapy is.
It doesn't indiscriminately poison and shatter DNA strands.
No. The anti-tumor effects we just detailed, the halted growth, the compromised blood supply, create a profoundly hostile environment. But a fully established macroscopic malignancy often possesses enough redundant survival pathways to weather that stress.
So it's a nutritional warfare tactic, not a localized nuclear strike. It weakens the fortress, but it doesn't necessarily obliterate it on its own.
Exactly. But consider the state of that tumor when the neoadjuvant chemotherapy is finally infused into the bloodstream. The tumor's vascular network is stunted, Its growth signaling is suppressed, the cells are metabolically starved, and their apoptotic pathways are primed on a hair trigger.
The cancer cells are biologically exhausted and stripped of their defensive mechanisms.
And at that precise moment of maximum vulnerability, the anthracyclines and taxanes arrive. The cytotoxic drugs hit cells that are completely incapable of mounting a defense or pumping the toxins back out.
Wow.
The calcitriol has exquisitely sensitized the tumor to the chemotherapy. The two interventions are deeply synergistic.
So the hormone holds the tumor down, and the chemotherapy delivers the lethal blow. That molecular synergy explains how an absolute gain of 19 percentage points is achieved. But understanding how vitally important this hormone is to our cellular defense systems makes the final component of the text feel like a public health tragedy.
It really does. The Biotechnology Guy article pivots from the baseline population is heavily deficient, but the text draws specific attention to the fact that oncology patients are at a vastly elevated risk of severe deficiency.
Right, because a cancer diagnosis fundamentally alters a patient's physical interaction with the world. The treatments are debilitating. Patients spend months convalescing indoors, in hospital wards, or darkened bedrooms, entirely removed from the ultraviolet exposure required for natural synthesis.
Compounding that lack of synthesis is a massive increase in metabolic demand. The sheer physiological stress of harboring a malignancy, combined with the immense toxic load of processing chemotherapy drugs, places an extraordinary burden on the liver and kidneys.
The exact organs required to hydroxylate inert vitamin D into active calcitriol.
Exactly. The metabolic machinery required to activate the hormone is compromised precisely when the body needs the hormone the most. The chemotherapy effectively drains the physiological reserves.
The implications of that are staggering. I mean, we have oncologists deploying highly toxic, incredibly expensive cytotoxic regimens, banking on those drugs to eradicate the tumor. Yet, the patients receiving those drugs are systematically depleted of the precise biological hormone required to make those drugs maximally effective.
We are sending the chemotherapy into battle without its most effective molecular vanguard.
It reveals a profound blind spot in the modern oncological paradigm, doesn't it? The medical establishment routinely funnels billions of dollars into developing the next generation of targeted synthetic therapies.
And these drugs represent genuine miracles of biological engineering, absolutely. But they exist within an ecosystem of extreme exclusivity.
Right. A novel antibody-drug conjugate can easily cost north of $150,000 for a single course of treatment. It requires advanced diagnostic profiling to ensure tumor compatibility, it demands complex cold chain logistics for transport, and it must be administered in specialized infusion centers by highly trained clinical staff.
The infrastructure required to deliver those highly engineered margins of survival ensures that they remain entirely inaccessible to the vast majority of patients in low and middle-income healthcare systems around the world. The cutting edge of oncology is heavily gated by economics.
Contrast that with the intervention analyzed in the Brazilian and Turkish trials. We're discussing a standard 2,000 IU daily dose of cholecalciferol.
A generic, non-patent compound that is synthesized globally by the ton. It costs mere pennies per dose.
It requires no refrigeration, no specialized infusion equipment, and no advanced diagnostic sequencing. It is an orally bioavailable tablet that is chemically stable on a shelf for years.
If the larger multi-center phase 3 clinical trials currently underway validate the massive PCR gains observed in these smaller cohorts, it won't just be a victory for tumor biology, it will represent a democratizing revolution in global oncology.
A physician operating a rural clinic with limited resources could instantly, exponentially increase the curative power of their baseline chemotherapy simply by prescribing a cheap supplement.
As the article concludes, if validated, this could be one of the most accessible ways to improve cancer outcomes worldwide. The emphasis is entirely on accessibility. It is the realization that optimizing the body's foundational endocrine environment can yield returns that rival the most sophisticated synthetic engineering.
It completely validates the core mission of Shubham Thorat and the Biotechnology Guy platform. They aren't just summarizing data, they are spotlighting the specific intersections where complex biotechnology yields profoundly simple, universally applicable solutions.
We have mapped a considerable amount of biological territory today. We started by examining the sheer volume of the global breast cancer burden and the brutal strategic necessity of neoadjuvant chemotherapy as a surgical pre-treatment.
We defined the ultimate diagnostic objective pathological complete response and explored why the current baseline rates of tumor eradication leave so many patients vulnerable to systemic recurrence.
We analyzed the clinical trial data out of FMB-UMS, observing how the addition of a daily cholecalciferol supplement drove absolute PCR rates from a baseline of 24% to an astounding 43%, a signal robustly corroborated by larger cohorts in Turkey.
And we descended to the molecular level, tracing calcitriol's journey to the nucleus to act as a genomic director, halting proliferation, triggering apoptosis, and suffocating the tumor's blood supply, perfectly sensitizing the malignant cells to the subsequent chemical bombardment.
It is a remarkable synthesis of epidemiology, molecular endocrinology, and clinical pragmatism.
It is a reminder that the most sophisticated interventions sometimes require the most foundational biological support to function.
Which leads directly into the final thought proposed by the source material, a concept that challenges the fundamental ethos of modern medicine. Medicine often looks for complex solutions, but sometimes the answer might be simple.
We spend our careers and our capital searching for the next synthetic silver bullet, assuming the answer must be engineered from scratch.
The question we must continually ask ourselves as we navigate the frontiers of biotechnology is this. In our relentless, heavily funded pursuit of the complex, the novel, and the highly engineered, the highly engineered, how many other profound curative mechanisms are currently hiding in plain sight? What other foundational biological keys are sitting quietly on the bottom shelf, entirely ignored, waiting for us to finally connect the diagnostic dots?
Are we so completely obsessed with building a better, more expensive hammer that we have forgotten to check if the foundational architecture is fundamentally sound? Thank you for joining us on this incredibly detailed journey through the research highlighted by Biotechnology Guy. Keep questioning the established baseline, stay fiercely curious about the world around you, and we will see you on the next deep dive.